In this video, I'm going to demonstrate how to carry out principal components analysis using scores on a set of summative measures. And one of the reasons why you would carry out principal components analysis is data reduction. For instance, let's say that my goal is, let's say I have a set of variables. Here, in this case, I have a set of 7 variables. I have subject matter interest, mastery, approach goals, perceived utility of instruction, anxiety, performance avoidance goals, work avoidance, and achievement. Let's say that I'm interested in predicting achievement from the previous set of variables. So, just kind of keep in mind, in this data set I have 100 cases, so I'm just going to run a quick regression and with achievement as my dependent variable. And so in this case I'm going to add in all of these other predictors here as independent variables and run the analysis. And you can see that my R-square value was pretty high, and it was statistically significant. You can also see that a number of these predictors were not statistically significant, and that's because they exhibited a fair amount of correlation amongst themselves. So, in other words, we may have some issues with collinearity among the predictors. So, and basically, when you run a regression analysis, you don't want to have a situation where you just throw in a whole lot of predictor variables because you can run into collinearity problems pretty quickly as the predictors are intercorrelated with each other. So one thing that you might decide is to sort of whittle down your predictor variables to a smaller subset. And one strategy that you could utilize is principal components analysis. So with principal components analysis, the basic idea is that you take a set of measured variables and you essentially try to derive a smaller set of variables that explain as much of the original variation in the measured variables as possible. And basically those latent variables are what are called components. So the basic idea is that if I could take the information, because basically these predictor variables from our previous regression are intercorrelated to a certain extent. So what I might be interested in doing is taking into account their overlap and deriving a set of uncorrelated predictors that could then be used to account for variation in my achievement measure. So basically, to carry out the principal components analysis, what I will do is in SPSS I'll go to Analyze, go down to Dimension Reduction, and then to Factor. So you're using the factor analysis program here. So my ultimate goal is to predict achievement. So what I'm going to try to do is essentially derive a smaller set of latent variables, or basically components, from this larger set of measured variables. And the components, when they are derived or extracted, they are uncorrelated with each other. So before I actually go about running the full components analysis, I need to determine if the correlation matrix that I'm working from if is indeed factorable, and whether it's indeed appropriate to even carry out components analysis, or if I was running standard common factor analysis, that too. So the way that I can do this, if I go under descriptives and click on KMO and Bartlett's test of sphericity, basically the KMO index is just one way of indexing the factorability of the correlation matrix. And then Bartlett's test is a significance test, basically testing whether there's essentially a significant difference between our sample covariance, our sample correlation matrix, and an identity matrix where essentially there are ones on the primary diagonal and zeros on the off diagonal, which is essentially like saying that you have a bunch of measured variables that are uncorrelated with each other. So what I'll do is I'll click on Continue here and then on OK. And you can see up here I've got the Kaiser-Meyer-Olkin measure. So this is the KMO right here. It's a measure of sampling adequacy. And then I also have Bartlett's test of sphericity. And so KMO values that are approaching 1 are really considered good. I would say that values in the 0.7s or above would be considered adequate to good. We actually have somewhat of a low value here, which is, so roughly 0.6, which is actually not a particularly good indicator that our matrix should be factored. But Bartlett's test of sphericity was statistically significant, and so this does suggest that we have a significant difference between our correlation matrix among our measured variables and an identity matrix. So that actually is better evidence that that it's appropriate to carry out our components analysis. So basically the KMO index is a descriptive index and Bartlett's test is a significance test. So at any rate, you'll notice that in addition we received some additional feedback in terms of principal components results. These were just basically utilizing the defaults in SPSS. So the defaults in SPSS for principal components analysis, first of all, if you click on extraction, you have the method, principal components. If we were going to run some other type of factor analysis like principal axis or maximum likelihood or so forth, we would click on one of those other options. But right now we're concentrating on components analysis. So what has to happen is that we have to decide on how many components help to explain or best explain the overall variation in the original set of measured variables. So over here where it says component, we have 6 components, and that's reflecting the fact that we have 6 measured variables. So the number of components that are initially extracted is equal to the number of measured variables. And so in this first column right here, these are what are called eigenvalues. And these are basically indicators of the amount of variation that each component accounts for in the original set of measured variables. So we could say that component 1, the first component, accounts for about as much variation in the original set of measured variables as 2.4 of those measured variables. The second component accounts for as much variation as 1.37 of the original measured variables. The third component accounts for less than the variation of a single measured variable, and that's why you have a 0.863 here. So you'll notice that the eigenvalues are decreasing, and it's reflecting the fact that you're accounting for decreasing amounts of variation in the original set of measured variables with each subsequent component that is extracted. In terms of the percentage of variance column, you have the percent of the variation in the original set of measured variables accounted for by each component. So the first component accounts for 40% of the variation. The second component accounts for 22%. The third component accounts for 14%. The fourth one accounts for 10%, and so forth. You also have a column for cumulative percentage. So the first component, the cumulative percentage, is going to equal this percentage right here that's accounted for by the first component, because the first component is going to explain most of the proportionally more variation than the remaining components. The second cumulative percentage reflects the sum of this percentage for component 1 and the percentage accounted for by component 2. So that gives us essentially 63.14 or 1% of the variation in the measured variables is accounted for by both component 1 and component 2. So these percentages are additive such that when you get to the 6th component, the cumulative percentage at that component is 100% because it's reflecting the sum of all the percentages from for the components that preceded it, as well as the percentage associated with that component. So basically, we have to decide on how many components to retain. In other words, how many components do we want to utilize in order to explain the original variation, and basically the variation in the original set of measured variables. So, we're essentially trying to kind of find the most parsimonious solution possible, which is that we're trying to kind of explain the most with the least. There are various decision rules or different decision strategies that can be invoked in order to determine how many components to retain. So one of the most common strategies, which is not necessarily the best strategy, but it is common, and it's also the default in SPSS, and that is to utilize the eigenvalue cutoff rule. Basically, the Kaiser criterion, it just basically says that we retain all components that have eigenvalues that are greater than 1. And what that means in the context of principal components analysis is that we are going to retain those eigenvalues that explain at least as much variation in the original set of measured variables as one measured variable. So with components that explain less than the variation of a single variable, those components are basically sort of lopped off, and we don't utilize those. So the default is the Kaiser criterion with eigenvalues greater than 1. So you can see right here that essentially that's the default. We can also utilize a scree plot in order to determine or to judge how many components to retain. So this actually provides us a visual strategy for deciding on how many components to retain. So we're going to start right there. We'll go to continue. And then, other options that you can click on in SPSS is, rotating component axes in order to help facilitate interpretation of those components that you actually retain. A common strategy is to utilize Varimax rotation. At any rate, for right now, we're not going to be so concerned with that. Right now, we're just focusing on how many components to retain. So, kind of clicking on this again, you'll see that in terms of my output, you'll notice that over here in this column, the extraction sum of squared loadings columns, you've got the eigenvalues for the first two components right here, and then there's nothing else following. And that's basically reflecting that eigenvalue cutoff rule of, well, we're going to retain only those components that explain at least as much variation as a single measured variable. So everything else is cut out of the picture. So using the Kaiser criterion, we would basically summarize the overall pattern or the overall variation in the original set of measured variables using two components. And so you can see the percentages and cumulative percentages are exactly the same as what we saw over here. So the cumulative percentage that's accounted for by components 1 and 2 is 63%. So the downside of the Kaiser criterion is that it can oftentimes lead to overfactoring. So we can also use other strategies to decide on how many components to retain. So we might utilize the scree plot. And the scree plot basically plots the component numbers against the eigenvalues, these initial eigenvalues that you see right here. So basically, if you think about this as the side of a mountain, what we're basically looking for is where the slope of the mountain really kind of peters out, and what we're left with at the base is the rubble. So to give you an example or another example, imagine that we had something that looked a little bit more like this. So let's say you had an eigenvalue for component 1 right here, an eigenvalue for component 2, right here, and then an eigenvalue for component 3, and on, you had something that looked a little bit more like this. So in this particular case, if we were to create our scree plot, you could see that it would look a lot more like this. And this would actually seem to suggest that, basically what we're doing is we're looking for where the eigenvalues sort of level off. And so in this case, it would look like that we have two principal components, and everything else is rubble. So we would sort of make the cut here and retain 2 components. In this particular scree plot here, it's a little bit trickier. There's certainly a dominant component, which we have on component 1. It also looks like there's a fairly dominant component on 2. But you know, the tapering off isn't quite as clear here as you see, or it's not as clear in our example data as you have right here. So you know, one thing that we might do is just kind of looking at this. You know, it's clear that, you know, the slopes from this point to this point and this point to this point are the greatest, and then you have sort of the slopes are not quite as dramatic for the rest of the eigenvalues. So I might be inclined visually to go with a 2-component solution based on the scree plot. But keep in mind that basically with the scree plot, it's oftentimes criticized for its subjectivity, because sometimes people can see 3 components as opposed to 2, or they might just see 1 component as opposed to everything else. And so, I mean, this is just the nature of the game when it comes to these kind of exploratory techniques, is that visualizing the data, sometimes people can have different interpretations on it. But just kind of looking at the scree plot here, I might be inclined to kind of stick with a 2-component solution, which actually happened to be consistent with what our original Kaiser criterion was suggesting. Let's say, for instance, though, let's say that what we had was something that looked a little bit like this, like with component 3. Let's say it, you know, it was, or let's say for component 4, you know, it looked like this. So you had this kind of tapering off down here. So imagine that it looked like this, and then, you know, kind of cut across here. Then I might be inclined to adopt a 3-component solution as opposed to the 2 that I'm going with right here. So at any rate, the scree plot is useful for kind of visualizing and deciding on the number of components to retain. And that's really the first big decision that you have to make when you're running the components analysis. There's another strategy as well, which is called a parallel analysis. So I just kind of looked up parallel analysis engine, and actually there's a nice one at this particular website right here. And parallel analysis, the basic idea behind it is that we have a plot of our original eigenvalues. This is from our data, and we want to make a plot of randomly generated eigenvalues. So the basic idea is that what we want to do when we plot out randomly generated eigenvalues, you know, it typically kind of follows this pattern right here, where essentially what occurs is that you have sort of a sloping of the line a little bit, and essentially it eventually crosses over the plot, if you will. And so so what we are essentially doing is comparing those randomly generated eigenvalues against the eigenvalues associated with our data. And so every, you know, the eigenvalues from our data that fall below what we would expect by chance, which is this reflected in this line right here, we would essentially shave off. And the eigenvalues that fall above chance, then we would retain those. So like if we had generated the random eigenvalues and it fell in this kind of pattern, we would be inclined to adopt a 2-component solution. If it had happened to be the case where it the line actually you know, kind of cut across maybe down, down here. This is really a poorly drawn. Let's try this again. Let's say it looked a little bit more like you know, this right here, then this would suggest, and this is not horizontal, just kind of pretend like it's got a little bit of a slope to it. Then we might be inclined to then adopt a 3-component solution. So the point is that, you know, some of these different decision criteria can lead to different conclusions about how many components to retain. It just so happened that using the eigenvalue cutoff rule and just kind of visualizing the scree plot, I went with the 2-component solution. But we can also test this out using parallel analysis. So the number of variables to be factor analyzed, remember that ultimately we were going to try to predict achievement. So we're only going to be factor analyzing these 6 items right here. So we have 6 items, and we had 100 cases. So basically, right here I'll put down number of variables 6. The sample size is 100. And so what's going to happen, and then type of analysis, the 1 is for principal components analysis. And so the basic idea is that what this will do is this will generate 100 correlation matrices or random correlation matrices, and the eigenvalues for the 6 components that would be extracted are computed for each of those. So literally there will be 100 component 1 eigenvalues, 100 component 2 eigenvalues, all the way through component 6. And so one way that we could summarize those, essentially what we've done is we would be generating an empirical sampling distribution of eigenvalues, and then we would take some value from those sampling distributions, such as the mean or the 95th percentile, which the default in this particular engine is to take the 95th percentile for the eigenvalues and then compare that against our data. So when I click on submit, you can see that these are the 95th percentiles for the randomly generated eigenvalues. These are the means for the eigenvalues. So essentially, if I go back to my my plot here, and actually you can just, first we'll just look at the actual eigenvalue. So you see that the eigenvalue for the first component is 2.419, which is larger than this randomly generated eigenvalue. So in that case, we know that we're going to at least retain the first component. The second eigenvalue is 1.369 from our data. The random eigenvalue is 1.27. So once again, we're above a random process here. The third component eigenvalue from our data is 0.863, and that's actually less than the randomly generated eigenvalue. So what that tells us then is that we're going to make the cut at 2 components. So you know, if I was going to plot this out just to kind of give a little bit of a visual representation here, the first random eigenvalue is 1.46. So you know, essentially for the first component, it's falling, you know, right around. I'm gonna put it right around here. The second one is 1.27, so it's gonna fall for that second component. You know, it may fall somewhere around here. The third one is 1.11. So when I'm plotting that out, you can see that's 1.11. So, you know, basically, and this shouldn't have a curvature in the line, but essentially, you know, it's going to cross over here. And then the next one is 1.01. So for this next component, it's going to be falling. So that was our first, our second, our third, which was 1.11. And then the fourth is 1, 2, 3, 4 was 1.0. So roughly, you know, roughly right around here. So you can see that the randomly generated eigenvalues cross over at this point here. So that would lead us then to retain these 2 components. So the point behind all, and so this is actually one of the better strategies for deciding on the number of components to retain. So the general solution in terms of the number of components to retain is actually 2. Now, so I don't really need to do anything else because basically all of my decision criteria kind of agreed. Sometimes though, you can have a situation where you might have using the eigenvalue cutoff rule, you might have let's say 4 components, and then the scree plot might suggest 2 or 4, and then the parallel analysis might suggest 2, and so then you've sort of got to make a decision among those different strategies which one to kind of go with. My inclination is to really go with the parallel analysis results. So at any rate, once you've sort of decided on how many components to retain, then you need to actually run it and force the number of components. So I'm going to force 2 here. And to tell you the truth, I don't need to do this because the previous analysis using the eigenvalues, it actually resulted in 2 components. So this is not going to change anything. But if I wanted to force, like, let's say I wanted to force a 3-component solution and basically retain these 3 components right here, then I could just click on fixed number of factors or factors to extract and click on 3, and then that would actually force a 3-component solution. So I'll quickly show you what I mean by that. So here you can see that this is forcing a 3-component solution. And so the point behind all this is that once you've decided on the number of components to retain to help explain the variation in the measured variables, then you have to actually go about the business of interpreting the components. So, forcing the 3-component solution, we have, you can see that we would have to interpret basically 3 components. Okay, there's the unrotated and rotated component matrices. But remember that basically we're going to stick with the 2-component solution, given the fact that we that our decision criteria led us to that decision. So I'm just going to go back and force the 2-component solution, which and then and keep the rotation on Varimax. I'm also going to click on loading plot to give you a visual of the component loadings. So at this point, you'll notice in the output that we've got a component matrix and a rotated component matrix. So actually, before I go into the rotated, let's just kind of click off of that for a second and rerun this again. So in this particular case, the component matrix represents the correlations between each of the measured variables and each extracted component or retained component. So you'll notice that the component matrix visually can kind of be summarized in this component plot right here. So you've got component 1 along the x-axis, component 2 along the y. And at the center, you have a 0 on component 1 and a 0 on component 2. So, and the range is from -1 to +1 on both components. So, visually what you can see right here is we can look at the plot for each of these measured variables. So there's subject matter interest. That's it right here. So you can see that it correlated negatively with component 1. So it's actually kind of going lengthwise from 0 to -0.624. And then on component 2, it's a positive relationship, so it's 0.57 on component 2. So you can see that we're going from 0 into the positive direction. So here you had the negative correlation, and here you had a positive correlation. And so you can see for let's see, anxiety right here, you've got positive correlations on both components. So you've got essentially lengthwise here, you've got the 0.712. So again, moving from 0 to 0.71 in this direction. So there's a positive relationship here. And then you can see on the next component it's 0.554, which is positive as well. Okay, so the thing about it is that what we do after we decide on the number of components to retain and essentially force our solution if we need to, is to try to name the components. And the components are basically uncorrelated latent variables, all right, and they summarize the variation in the original set of measured variables. And so what we utilize is the component matrix, or following rotation, the rotated component matrix, in order to interpret or name those components. So subject matter interest, you can see, correlated really highly with +1 and correlated highly with +2. Mastery approach goals correlated highly with 1 and so forth. And you can see really there's a lot of heavy cross-loadings between these two. And generally when you're interpreting whether or not a measured variable is loading onto a component, enough for you to deem it as useful in naming the component. There are various thresholds that have been given, but we're just going to adopt a loading criteria of 0.30 in absolute value to decide on whether or not to name a given component based on a particular measured variable. So you can see in this particular case, really, the measured variables met the inclusion criteria on both components. So that really raises some questions about, well, what do we do? Optimally, we would want our measured variable to define one component and not be used to define the other component. And this is one of the problems that we can run into if we don't perform a rotation of our data. Or excuse me, not the data, the actual coordinate axes from our component plot. So basically, you can see right here, and this is a really good illustration of why you would consider rotation, is that you can see that the distances, along the x-axis, the distances to these sets of measured variables are about the same when it comes to both components. So essentially then that's why you have such great difficulty in terms of naming the components based on a given measured variable. So one thing that we might consider doing is to rotate the coordinate axes. So the axes, basically the idea is this: we leave the data points, or we leave, the measured variables in the same relative position. We don't move them around at all. Okay, so we're not playing fast and loose with the data. We're leaving those coordinates essentially the same. And what we do is we rotate our axes to a certain amount, and essentially redraw the lines such that they fall through the data points, perhaps in this kind of way right here. So essentially, what this allows us to do is, you can see, and imagine these are actually straight lines as opposed to this horrific drawing here. But you can see that lengthwise, they're much more related to, in this case, this group would be related to component 1, and these right here lengthwise would be related to component 2. And so if we perform what's called a Varimax rotation, the coordinate axes remain perpendicular, meaning that the rotated components are actually remain uncorrelated with each other, but it makes it easier to interpret the relationships between the measured variables and the components. So to do that, that's where we just basically, when we run the analysis, that's why we clicked on rotation and we clicked on Varimax. So this is one of different, a number of different rotational strategies. Varimax maintains the orthogonality of the original components while rotating those axes. Some of the other options are still orthogonal, but then there's also like Promax and Oblimem that allow correlations between the components. But we're not going to focus on that in this particular video. So I've just clicked on Varimax rotation, and so in this particular case, you can see that now we get a rotated component matrix. And so now let's compare that against the original component matrix. So with the rotated component matrix, you can see that subject matter interest correlates really highly and positively with component 2 and negligibly with component 1. Mastery approach goals correlates highly and positively with component 2 and pretty small correlation with component 1. Certainly not meeting the inclusion criterion of 0.30 in absolute value. Perceived utility correlates highly with component 2 and negligibly with component 1. So, right there you can, and then when you look at anxiety, performance avoidance, and work avoidance, you can see that all of these correlate most highly with component 1, and pretty negligibly with component 2. So what this means is that I would use these 3 variables right here and name component 2 based on these 3 measured variables, and I would name component 1 based on these 3 measured variables. So I might name component 1, given that it really seems to be heavily defined by anxiety avoidance and work avoidance. I'll just refer to this as avoidance motivation. Okay. I'll just put a little V down here for avoidance motivation. And for component 2, these really kind of reflect an approach orientation towards learning. So I'll just call this just generally approach motivation. So essentially, I now am able to summarize the variation in the original set of measured variables in terms of 2 components that really seem to account for that, which is approach motivation and avoidance motivation. So you'll notice that when we scroll up a bit, you have essentially rotated sum of squared loadings. So we have eigenvalues for each of those rotated components, the percentage of variance and the cumulative percent of variance accounted for. And basically after rotation it redistributes the variation accounted for by each of the components. So the cumulative percentage, it remains exactly the same. So you're not going to be accounting for more variation in the measured variables than you were originally. But you can see that in terms of the percentage of variance accounted for, it sort of oftentimes it ends up kind of evening things out a little bit more relative to the unrotated solution. So at any rate, one other thing to kind of note is, the communalities up here. The communalities are basically reflecting the proportion of variation in the measured variables that's accounted for by the components. So subject matter interest, the original communalities are all going to be 1s, and that's because it's essentially taking into account the fact that we've extracted 6 components that's equal to the number of measured variables, and those 6 components cumulatively will account for 100% of the measured variance in all of our measured variables. After deciding on a subset of those components to retain, then you can see that this is a proportion of variation accounted for by the subsets. So you see that subject matter interest, the 2 components accounted for about 71.3% of the variation. Mastery approach goals, they accounted for about almost 50% of the variation. Perceived utility accounted for about 62.6% of the variation, and so forth. And in fact, if we go down to our matrices right here, remember that our component matrix and rotated matrix, this is pre and post rotation, but keep in mind that they are orthogonal, meaning that the components themselves are uncorrelated with each other. So if I was to take here, for instance, let's say take this loading right here of 0.842 on the rotated matrix, 0.842, and square it, then essentially that component accounts for about 0.708 or roughly 0.71 or 71% of the variation or the total variation in subject matter interest. The second one, if we take 0.072 and negative and square it, then that gets us 0.005. So if we add that to 0.708, then that leads us right back up here, and so our communality is 0.713, which is the percentage of variation that we just found here. Note too that we would have the same proportion, the same communality if we square these 2 coefficients here and sum them up. We would end up with the same communality of 0.713. So at any rate, that's what the communality estimates are basically driving at. Now, we still are in a situation we wanted to reduce our original set of measured variables down to a subset so that we could run our regression analysis and predict achievement. So what we can do is essentially go to back to dimension reduction. If we click on scores, we can request component scores. which is basically a score on each component for each person within our data set. So if we click on Save as Variables and we'll click on Regression, Continue, when we rerun the analysis, it's the same results as what we had before, but now in our data set we've got component 1 and component 2 scores for each person. So, and we can actually, if we double click on this, let's just go ahead and change it. We called the first one, the first component, we called it avoidance motivation, and the second one we called it approach motivation. So now these two components are uncorrelated, like I said. So if I was to run this and just ask for the relationship between these two component scores, you can see that essentially they're uncorrelated. So actually they're going to account for additive variation when it comes to predicting. I'm going to take this out too as well. When it comes to predicting variation in achievement. So what I'll do is go to Analyze, Regression, Linear, and now instead of having achievement in here and all of these other predictors, I'm just going to reset it. I'll put approach and avoidance into as predictors and achievement as my dependent in my dependent box. Click on OK, and so now we have the R-square value is 0.231. So we can see that that's statistically significant. And when we look down, we have approach motivation being significantly positively related to achievement, and avoidance motivation being significantly negatively related to achievement. So this is clearly a more parsimonious solution than when we ran the regression analysis, where we included all of our predictor variables and where there were a number of intercorrelations among the predictor variables. So that is essentially an illustration, or this has just been an illustration of how to utilize principal components analysis as a data reduction technique, in this case in order to generate a smaller set of predictor variables for inclusion in a regression analysis. You can also use components analysis in the same way if you wanted to reduce the number of dependent variables to a smaller subset for inclusion in a MANOVA. So at any rate, I hope this was you found this helpful, and I'll be working on more videos. So